So what is next we are seeing what is Starling hypothesis and Starling forces. So determination of net filtration pressure is based on the Starling hypothesis. The Starling hypothesis states that the net filtration through capillary membrane is proportional to hydrostatic pressure differences across the membrane minus oncotic pressure differences. So based on the Starling hypothesis, the net filtration through the capillary membrane is proportional to the hydrostatic pressure differences across the membrane minus the oncotic pressure differences across the membrane. Hydrostatic pressure within the glomerular capillaries is the glomerular capillary pressure. So hydrostatic pressure means which is the glomerular capillary pressure. Okay, that is how much? 60 mm of Hg. Then all the pressures involved in the determination of the filtration are called Starling forces. So there are so many pressures are involved in the filtration process. That is glomerular capillary pressure, colloidal osmotic pressure, hydrostatic pressure and net filtration pressure. All these four pressures together known as Starling forces. So that is regarding the Starling hypothesis. The next we can discuss regarding filtration coefficient. What is the filtration coefficient? Filtration coefficient is the GFR in terms of filtration pressure, net filtration pressure. So we are representing the GFR, that is glomerular filtration rate, in terms of net filtration pressure is known as filtration coefficient. It is a GFR per mm of Hg. Okay, GFR per mm of Hg of net filtration pressure. For example, when GFR is 125 ml per minute and net filtration pressure is 20 mm of Hg. So as per the definition of filtration coefficient, it is the GFR per mm of Hg of net filtration pressure. Okay, so here there is 20 mm of Hg. So 125 divided by 20 mm of Hg, that is a GFR per mm of Hg of this net filtration pressure. So GFR is 125 ml and the net filtration pressure is 20 mm of Hg. So that the filtration coefficient is 125 divided by 20 mm of Hg, that is 6.25 ml per mm of Hg. The next topic is factors regulating or factors affecting the GFR. Okay, so there are so many factors which can affect some the glomerular filtration rate. Let us see what are the factors. First one is renal blood flow. So it is the most important factor which is necessary for glomerular filtration. GFR is directly proportional to the renal blood flow. Okay, so GFR is directly proportional to the renal blood flow. Normal blood flow to both kidneys is 1300 ml per minute, which is about 26% of the cardiac output. The next factor is tubuloglomerular feedback. What is that? Tubuloglomerular feedback is the mechanism that regulates GFR through the renal tubule and macula densa. So it is a feedback mechanism that can regulate GFR through renal tubule and macula densa. Macula densa of juxtaglomerular apparatus in the terminal portion of thick ascending limb is sensitive to sodium chloride in the tubular fluid. So that portion we have discussed regarding macula densa in the last class. So macula densa is the terminal portion of the JGA, that is juxtaglomerular apparatus, which is seen in the thick ascending segment, and that is highly sensitive to the sodium chloride of the tubular fluid. Okay. When the glomerular filtrate passes through the terminal portion of thick ascending segment, this macula densa acts as a sensor. So as a filtrate, that is glomerular filtrate, passed through the terminal portion of thick ascending segment, what happened? This macula densa, which is highly sensitive to the sodium chloride, can be act as a sensor. So that detects the concentration of sodium chloride in the tubular fluid, and that can accordingly how much chloride or how much sodium chloride is contained in the tubular fluid. Based on that, it can alters the glomerular blood flow and GFR. So that is about the tubulo-glomerular feedback, which is the second factor which regulating the GFR. Then third factor is glomerular capillary pressure. Glomerular filtration rate is directly proportional to the glomerular capillary pressure. Normal glomerular capillary pressure is 60 mm of Hg. When glomerular capillary pressure increases, GFR also increases. Okay. Then fourth thing is colloidal osmotic pressure. We have already discussed regarding all of these pressures. Colloidal osmotic pressure, it is we can already know regarding this colloidal osmotic pressure, because it is inversely proportional. It is one of the opposing pressure for the filtration, so it will inversely proportional to the GFR. Okay, let us see. Glomerular filtration rate is inversely proportional to the colloidal osmotic pressure, which is exerted by the plasma proteins in the glomerular capillary blood. Normal colloidal osmotic pressure is 25 mm of Hg. When the colloidal osmotic pressure increases, as in case of dehydration or increased plasma protein level, then what happens? GFR gets decreases. Okay. When colloidal osmotic pressure is low, as in case of hyponatremia. So in hyponatremia in cases under the colloidal osmotic pressure, so there is no proteins presence. There will be decreased colloidal osmotic pressure. So what happened is there will be increased GFR. The next factor, that is fifth factor which affects on GFR, is hydrostatic pressure in the Bowman's capsule. So as we have already discussed, GFR is inversely proportional to this, because this hydrostatic pressure is one of the opposing pressure for the filtration process. So normally its normal value is 15 mm of Hg. The next factor is constriction of afferent arterioles. Constriction of afferent arteriole reduces the blood flow to the glomerular capillaries, which in turn reduces the GFR. Then the next factor is constriction of efferent arteriole. If efferent arteriole is constricted, initially the GFR increases, but so that increased GFR in initial time is due to the stagnation of the blood in the capillaries. So as the blood flow to the arterioles increases, efferent arterioles increases, there may be stagnation of the blood in the capillaries. So as a result, the GFR will increases. But later what happens means, when all substances are filtered from the blood, further filtration does not occurs. Okay, so gradually what happens, this filtration process continues and all the substances are filtered from the blood. So what happens means, further filtration does not occurs, and this is because the efferent arteriolar constriction prevents outflow of the blood from the glomerulus, and no fresh blood are enters into the glomerulus for filtration. So after filtration and all, what happened is the efferent arteriole constriction can prevent the outflow of the blood from the glomerulus. So what happened there? No fresh blood enters the glomerulus for filtration. No any fresh blood can enters the glomerulus for filtration. Then another factor is systemic arterial pressure. Renal blood flow and GFR is not affected as long as the mean arterial blood pressure is in between 60 to 180 mm of Hg due to the autoregulatory mechanism. Yesterday we have seen the autoregulatory mechanism of the kidney. So when the mean arterial pressure is within the range of 60 and 180 mm of Hg, there will not be any effect for the GFR rate. But any variation in the pressure above 180 mm of Hg or below 60 mm of Hg can affect the renal blood flow and GFR. The next factor is sympathetic stimulation. Okay, afferent and efferent arterioles are supplied by the sympathetic nerves. The mild or moderate